difficult, and make sure you get used to it, okay? So last time we defined the dipole moment, and it's a vector. And a typical mistake, students forget to the vector goes from the minus to the plus, not plus to minus, minus to plus. And the magnitude is the charge in Coulomb times the distance in meters. Okay, so that distance is between the plus and the minus. And both charges have the same magnitude. And we use that because in chemistry you have a lot of bipolar molecules like water, chlorhydric acid is another example, or molecules that can get polarized but not permanently. So that's why they use this, because otherwise the distance is so small between the two poles. Okay, and then we learned that if you have a dipole, whether it got polarized or it's permanently polarized inside an electric field, it will be acted upon by a torque. Okay, so the electric force will apply a torque, and the dipole wants to align itself with the electric field. Okay, so it wants to rotate, align itself with the electric field in such a way that the potential energy will be minimum. Okay, so that's the way we can find out which way it's going to rotate. It's going to rotate in such a way that the dipole, which is a vector, will align itself with the electric field. So they will have the same direction. Okay, so we did that. That will be the magnitude of the dipole. You see, oh, it's annoying. The echo is annoying. Hello, hello, hello. Okay, and that will be the magnitude. Okay, it's a cross product. That will be the potential energy of the dipole. It's going to be minus because it wants to be the minimum potential energy. Okay, so when the dipole is aligned with the electric field, the potential energy is minimum. If it's anti-parallel, it will be maximum. In between, it will be zero because we decided this way. Okay, and now we're going to talk about the electric flux. Okay, and also I recommend that you check your textbook here. So for example, page 708, it's going to show you that if you have a charged particle inside an electric field, it will be acted upon by a force, but that force here is along the electric field. So if it's positive, it's going to be along the electric field. So you see, it's going to follow a tangent. Okay, so the force will be tangent to the electric field line. So if you have a line like this, the force will be tangent. If it's a negative charge, it will be anti-parallel, because a negative charge always wants to go against the electric field. Okay, so maybe I didn't make that clear. And if you scroll down, so I can scroll down page 709. Okay, so this is a dipole here. See, so if you use castor oil here and you have a grass seed, so it's an insulator, but it gets polarized. So the plus wants to go with the electric field, the minus wants to go against the electric field. Okay, so it will be acted by a torque in such a way, again, that the dipole moment going from minus to plus will align itself with the electric field, even though it's not charged to begin with. So this is the way we can visualize the electric field lines. Is that clear? Polarization is very important for the human body because the way, for example, an impulse is traveling along a neuron is through polarization, depolarization, polarization, depolarization, from the brain to the fingers, for example, or from the fingers to the brain. So everything is about polarization, depolarization. The heart also. Okay, and what else? So I'm going to go down. It's a very, very nice textbook. So you see here, if you have a dipole, here. Plus wants to go with the electric field, minus wants to go against the electric field. This is your vector, the dipole moment, and it wants to align itself with the electric field. So you're going to have a rotation clockwise. So you take your right hand, rotation clockwise. The torque, which is a vector, goes into the board, clockwise into the board. So there will be one question like this for the test number 1 about dipoles. Okay, so here you have the definition. Okay, blah blah blah. So here they show you how to find the potential energy. So potential energy, and we're going to get to that in the next unit, is the work that you have to put into a system to change the configuration. So you have a mass and you have the earth. I'm going to do work against gravity. So the work I am doing on the system earth book is going into the potential energy, which is mg times h. Okay, so using the definition of work, you can find what's going to be the potential energy. So if you have a dipole moment which is aligned with the electric field, if you want to change the configuration, you have to do work against the electric field, and the work that you have been doing goes into the potential energy. So that's the definition, and you end up with a dot product. So it's a scalar. Okay? Okay, force, blah, 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 blah. Okay, so you can do that. These are solved problems. And now here they show you how to find the electric field here at a given point along the axis. Okay, we already did that. We did that also for a very long distance, so very far away. You see, it's 1 over the distance cube, not square, because very far away plus and minus cancel each other. But you can see the computation that they did. Okay, you have to use. There was another problem here. So they start from here, and then they're going to simplify at a very, very large distance, which is always the case with molecules. For example, in chemistry, at a very large distance, they use what is called in math a binomial series, if I remember, or a Taylor series. So they have to expand, and up to you to do it because you are into calculus, and that's what they get at a very large distance from the dipole along the axis. So again, it's very easy to get this book. It doesn't matter which publication you get. Okay, you can find $5, $10, very easy to get. It's a very, very nicely written. It's very important for engineers. So when you have a textbook, what do? First thing, you skip to the summary. Okay, so you don't read. You don't read like from beginning to end. You skip to the summary and you look at all the most important points, right? The most important concepts. So Coulomb's law, electric field, superposition principle. So you know what they are talking about. Once you have read the summary, you go back and you look at the pictures that you have in the chapters and you read along, right? To really ask yourself questions to reflect on what it says. And then you can read and do the solved problem. Okay? One way to do it also, maybe not necessarily in physics, but you download one chapter at a time, you upload in ChatGPT, and you ask ChatGPT, okay, summarize everything. And then you get a very nice summary, right? As long as there is AI, you can use it. Okay, so that's all I had to do. Page 732. Okay, so now we are at Gauss. Gauss law. So Gauss was a mathematician he's the one who came up with the Gaussian curve, you know, the bell curve. So it's a mathematical tool for us to compute the electric field when you have a nice symmetry. Spherical symmetry, like the Van Graaff generator, a cylindrical symmetry, like a wire which is charged, or symmetry like a flat surface that is charged. So it's a mathematical tool, but it's just a way to use Coulomb's law. So Coulomb's law says it's inversely proportional to the distance squared. Okay, so you multiply the distance by 2, electric field will be divided by 4. Okay, so I was trying to explain that last time. It's not easy. It's not easy. It's a mathematical concept, so I'm going to try to make it easy for you. Okay, so remember the plasma globe, right? So here you have a Tesla inside, Tesla coil inside. So this here will get charged. So imagine this is charged, this is positively charged. And inside you have plasma, so you can visualize the electric field. As you increase the charge, because you increase the voltage, say, you're going to increase the number of lines if you want to visualize. And that means the electric field will be stronger because it depends on the charge, right? That makes sense? And you can use the density of lines. So if you have more charges inside here, you're going to have higher density. So you're going to have more lines. So far, so good? Okay, and then here you have the globe. The globe is a closed surface. It's 2D, 4 pi r squared, but it's a surface. So now you have to imagine it's like a bag. So in that case, it's a spherical bag, but you can take any bag you want. So in that case, it's going to be spherical, right? You have a bag here. So you can define the number of lines poking through this invisible imaginary bag. So that imaginary bag, that's what we call the Gaussian surface. Now, the number of lines poking through this surface is called the electric flux, the electric field flux. It's called the flux. Okay, so the flux will be the number of electric field lines poking through this surface. And last time we understood that it only depends on the charges inside, the amount of charge inside your bag. If you multiply the charge by 2, it makes sense to you that the number of lines poking through will be also multiplied by 2. So Gauss' law says that the number of lines poking through a closed imaginary bag depends solely on the charge inside that bag. So it will be Q inside the closed bag divided by epsilon 0, which is a constant. Okay, now the size of your bag does not really matter, because if you take a small bag here, or if you have a big bag, you see that the number of lines does not change. Would you agree? You have the same lines poking through. Agree? Okay, it's like a source. So it's like a hair dryer. Okay, you have air blowing away. So you have the same amount of air blowing through this or blowing through that. Okay, so we're going to see that number of lines depends. It's going to be the area times the electric field. Okay, I will show you that with water, for example, but that will be the definition of an electric flux. Okay, the flux of the electric field, it's the area, okay, the area through which the lines are poking through times the magnitude of the electric field. So if I take this bag here, it will be 4 pi r squared times the magnitude of the electric field at the surface of the bag. Are you with me? So here, if I take this big bag here, the flux will be the area of the bag times the magnitude of the electric field at the surface of this bag. And why does it the flux only depend on the charge? Because if you, for example, you divide the distance by 2, so you take a small bag, so the radius is divided by 2, the area will be divided by 4 because it's 4 pi r square. But the electric field is much pi by 4 because of the distance square, inverse distance. The inverse square law. You with me on that? So you multiply by 4 divided by 4, the flux stays the same. Okay, so it doesn't matter the shape of your bag, the number of lines poking through will not change. Okay? So the idea is to take a nice bag. You want a spherical bag, you want a cylindrical bag, but you don't want to have any bag because otherwise it get very complicated. Okay, so we're going to see, just to show you the idea. Right? I don't know where I am. I am here. Okay, so again, let's go back to my Tesla coil. So this is charge. Now I can, instead of having a nice spherical bag, I can take this bag. Okay, so it's a bag. Imagine a plastic bag, but it's closed. Okay. Now it's very hard to visualize the electric field because it's going to depend. Maybe it's going to be this way, but here maybe the electric field will be that way. So here the electric field here all of a sudden has two components. One component here and one component there. So it will be perpendicular here and parallel there. Okay. And then at another distance, it has also two components. So maybe it's going to be this way, the electric field here. So it has two components, perpendicular and parallel. But the number of lines, the total amount of lines poking through still will be the same. Okay, because you have the same source. Okay, you have the same amount of water flowing through, poking through that bag. So the flux here will be the same. And that flux, okay, will only depend on how many charges are inside. So it will be inside the bag over epsilon 0. That's not going to change. Now, if you want to do the math, and that will apply to, for example, hydrodynamics, like if you study the motion of water or fluid, you're going to use the same equation to find the number of lines. Then it becomes all mathematics because you will have to find the sum, okay, of here the electric field perpendicular times the small area here, delta A. Okay, so you will have to divide your surface in small element, surface element, right? And then it becomes a headache. Okay, because that perpendicular means that you only take, it's going to be a dot product. It's a long, I will show you a video, but you're going to get an equation like this. And that will be the definition of flux. But we will never have to do that, okay? Because we only use nice bags, right? Like a sphere. So we don't have to worry, but that will be the definition. Okay, so the units for the flux, it depends. So the units for the flux here, that's going to be, the electric field is Newton per Coulomb, and then meter square. Okay, so that will be the definition of the flux. Okay? So this is Gauss law. Okay, so Gauss law says that the number. So if you want to explain conceptually, it just depends. It says that the number of lines poking through a closed bag only depends on the charge inside. Mathematically, you're gonna translate this sentence by this integral, which is a surface integral. Yes.
Do you mind explaining the equation part on what you wrote again?
This is what we're gonna get back to that. That
The one right about that one here.
here,
The one down.
this one.
The one that has that one.
Okay, so that just means to compute the number of lines poking through a closed surface, you have to divide your, I will get back to that, but you have to divide your surface in small, tiny delta A. Okay, and we're going to scan through. So that will be the definition of flux. Okay, but I will get back to that. I have a nice video to show how it works. But for now, remember, the electric flux is easy to compute. It's going to be whatever is inside that imaginary bag. Okay, so the charge inside divided by epsilon 0. When you translate that using mathematics, that's what it comes to. So this here, this equation, you apply that to, for example, a fluid that moves with a velocity v. So instead of having the electric field, you're going to replace the velocity of the fluid, but you will use exactly the same equation. Okay, so for example, flux for water, right? I'm going to do it step by step. We can define the flux as the amount of stuff flowing through an area. That area can be closed. That's how we use Gaussian law, or it doesn't have to be closed. So, for example, if you are studying fluid mechanics, okay, and you have water flowing, you can imagine an area A, and the fluid is flowing with a velocity v. Okay, so it means imagine you have an area here, and you want to know how much fluid will went through. Are you with me on that? Okay, what's the volume of fluid going through this area? Volume is area times the distance, right? Times the height, yes? You have a cylinder. The cylinder is the area times the height, yes? So the amount of volume, okay, the volume of water flowing through this, okay, it's going to be the area, okay, times the height. Agree? During a time t. During a time t, you have that amount of water flowing through this area. If the fluid goes really fast, the volume will increase. Agree? Now you can define the volume per unit time. The volume of water flowing per unit time. So you're going to divide by the time, right? That's going to be A delta x over delta t. And what is delta x over delta t? Velocity. So you see that the flux in that case, so the amount of water flowing through this area is just the area times the velocity. And the velocity is your vector. Okay, it's a vector. Good. So in that case, the area is just perpendicular to the velocity, so we're going to write this way. Now you can do the same thing for light. You can find the amount of light, okay, or the amount of radiation. So let's say you have uranium and you have radiation. You can define the amount of radiation going through an area A. That will be also the flux. Okay? Okay, so let's try to understand that because it's such an important concept. Okay, let's say you have water flowing. Now, first of all, from your calculus class, you see when you have an area. So this is an area. Do you all agree it's in 2D? I want to define its orientation. I want to know which way it's being the orientation, right? How it's being tilted. This is this way, or that way. So in mathematics, the way they do it, they define what we call the normal vector. So normal means perpendicular, and they're gonna glue that vector here. It has a magnitude of 1, just so we understand how this area is oriented. Does it make sense? This normal vector has coordinates. It has a magnitude of 1. So that way I know, once you define the normal vector, you know how is it positioned. Does it make sense? Okay? So that will be in geometry or, I don't know, some kind of calculus. So n hat, okay, it's called the normal vector. Yes, it's a small vector perpendicular. So normal means it's not that you have abnormal, that there is something wrong about those vectors. It just means it's normal means perpendicular. That's what it means. Okay. There is no abnormal vectors. Okay, so let's say you have water flowing. So you have a fluid here and it's flowing this way. And maybe inside that fluid, you have those little what it's called, plankton, like little things here flowing. Okay, flowing with it. So they have a velocity v. Okay, so you have little shrimps. Yeah, you go and you want to catch the shrimps because you have a whale and you need to feed the whale, something like this, right? Okay, and I want to define how many of them I'm going to catch. So I have a net. So how can I increase the number of little shrimps? I have a net. You have 3 things. So do you take, what do you think? What will make, you want to catch as many shrimps as possible? So the velocity, you mean?
Oh, sorry, yeah.
Yeah, very good. So if I have a net here, okay, I have a net. If I want to catch more of them, if they go really fast during a given time, I'm going to catch more of them. Does it make sense? Very good. So it depends on the velocity. I agree. Okay, so if it's flowing very fast during the same amount of time, I catch more stuff. You have more flowing through this area. Okay. What else? Very good. You can increase the area. Okay, so if you have a small area, okay, I'm not going to catch as many shrimps. So it depends on the area. Okay, and we have this little. So in that case, we don't have choice. Only you have choice. I can decide that the normal, I can define a normal vector going this way, but it could be the other way. So it's up to you. You decide. If it's a closed surface, you're going to see you don't have the choice. So what else it depends on?
The angle of the net?
Very good, very good. What's your name?
Ronnie.
Ronnie, exactly. Like if I put my net like this, right, you're not going to catch as many shrimps. You know that. You don't need to take physics, right? Your guts tell you, no, that's not a good idea. We are not going to get some dinner tonight. Not good, right? And if you place your net like this, are you catching any shrimps? Nothing, right? So it depends on that, I don't know which, okay? So the velocity is this way. So it depends on that angle here, this angle here, theta. Okay, so theta will be the angle between the vector and the normal. Are you agree? Okay, so if you see the angle is 90 degrees, what's going to be the flux? Zero, very good. So the flux equals 0 when the angle equals 0. So we need a mathematical function that tells us if the angle is not 90 degrees, right? This is 90 degrees, sorry. When the angle is 90 degrees, there is nothing going through the net. So we need a mathematical function that is 0 when the angle is 90, and that is maximum when the angle is 0. Cosine, exactly, cosine. So here the flux will be cosine theta, exactly. And how we define in math, when you have a vector magnitude, the magnitude of one vector times, this is also a vector, A is a vector actually. The area, we can say it's a vector, okay? Or you can keep n hat. So that will be equation sheet here, something, two vectors with a cosine. Do you see? It's a dot product. It's a dot product. You see how we can use math? Like calculus was invented by Newton because he needed calculus to develop his law of gravitation. So it's just a tool to be the slave of physics. So it's going to be V dot, we can say n hat, and then you multiply by A. Or you can say A dot V, the velocity. Okay, so you see how we can use math. Because we want to define the number of little things flowing through an area, or we can define the flux as a number of field lines poking through an imaginary bag. If I go back to here, so it's not easy, okay? I'm not saying it's easy. You see, the electric flux, the flux for the electric field is going to be the electric field E times the area times the cosine between the area, the normal vector, and the electric field. And then at some point, you know, when the electric field is not uniform, then it has to be an integral because you have to sum up. But you don't have to worry about it. But you see, it looks cool. The electric field flux, it's going to be the charge inside your bag over epsilon 0. Okay, so another thing I forgot to tell you is that, so this is an open area. So when you have an open area n hat, you can take it this way or the other way. But if you have a closed area, so this is a bag, it's 2D. Okay, so in that case, the convention is to take the normal vector for a small, so that will be a little square, like a very small area delta A, and hat has to be out by convention. It's still perpendicular. Okay, and then you can divide the whole area as a sum of delta A, right? You can divide the whole thing like little scales. It's like scales. Okay. So it's a mathematical concept. So let's see if I have I'm doing Gaussian, Gauss law. So that will be the flux for a fluid like water. So the same idea.
So the flux or flow rate is equal to the velocity v times the area A. However, if the area element is tilted with respect to the direction of flow, less of the water passes through it. So flux depends on the angle between the P field and the area element. Define the area width.
So by the way, maybe in math, you see that you can learn that you can define this area here because now the fluid is going through this area here. You see? It's like a projection. And this area here is just A times the cosine theta. So it's a projection. You are projecting this area here onto there. So that's why now the number of fluid going through depends only on this area here. Okay, so you can project, it's like the component, you can take the component of a surface area.
Find the area. Found by hand.
So you see, you're scanning through and you only take in account the component of the electric field along the normal vector. So you scan through. So when you are taking an integral, so this is a double integral because it's through the area, what you are doing, you are scanning through. Yeah.
I was gonna ask, why is it a double integral?
Because it's a surface integral. So for example, if this is the x-axis and this is the y-axis, so that will be a small area can be dx dy. So you have to integrate over x and integrate over y. And then you can use cylindrical coordinate or spherical coordinate. Yes.
That will be like a
Yeah. Yeah. So in that case, it's an open area. So that applies to any field, like water flowing, like radiation or light. Now, in our particular case, we're going to take a closed area. So it's still an area, okay, but it's going to be closed. Because then we can say that that flux only depends on the charge inside. But this is just the mathematics. So it's going to get to that. So when you are integrating, that's what you are doing. Okay, you divide your area in small delta A. Okay, and you add.
The idea is to find the total number of lines of force. Expression of flux is the same for all vector fields. But all fields are not created equal when flux out of a closed surface is considered. Imagine a surface that completely encloses a volume inside a volume. No matter the flow rate, whatever quantity of water.
So what do you think the flux is now? Zero, very good. Because the number of little shrimps going in equals the number of shrimps going out, so the flux is going to be zero. It doesn't diverge, it does not converge. So the number of field lines going through a closed surface, in that case, it's not an electric field, in that, I don't know what it is, water, let's say, then the flux equals zero.
Same is true in the case of magnetism. net magnetic flux in a closed surface is always equal to zero.
Do you see why? Because you have a magnet, so you have the north and the south. The magnetic field lines will go from the north into the south. So there is no source inside. Whatever comes out comes back in.
It's proportional. Okay. Inside.
And that has to do with the divergence, right? When you take calculus, there is a source inside, so you must have lines poking through that closed surface. And the physics comes and says it's going to be the charge divided by epsilon zero because it's a consequence of Coulomb's law. So by convention, if it comes out of the bag here, the flux is going to be positive. If you have a bag and some reason it flows in, that's going to be flux will be negative. And if you have as many flux lines in that you have out, the flux will be equals to zero. So you have to imagine water flowing.
So epsilon zero like never changes, right? In that
So for physics, the electric field flux will be Q in whatever is inside over epsilon zero. Epsilon zero is just a constant. Okay? And it's a consequence of Coulomb's law, but it's a very elegant way to express it. Okay, this one, okay, Gauss law. Okay, so again, the flux depends on, of course, how strong is the field. So for example, if the water is flowing faster, the velocity is larger, so you're going to catch more water during the same amount of time. It depends on the tilt, so that will be the cosine between the normal and the vector, and it depends on the size of the area. So again, this is called the normal vector, okay, and it's perpendicular to the surface, and the magnitude is 1. Yes.
This doesn't have like has to be necessarily positive, which can also be negative. It's not an absolute value.
Yes, so the flux can be, it's a scalar, but it could be negative.
Oh.
So if you have a negative charge, if you have a negative charge, the flux, so the charge will be like a sink, right? So it's flowing in.
Yeah.
So in that case, you're going to get a negative flux. Okay, it's a good point. A negative charge is a sink, a positive charge is a source. Okay, so by definition here, the flux here going through this area will be E times A times the cosine between them. Okay, it works for vector field. So a field is when any point in space you can define a vector. The normal force is always, if it's a closed surface, it will be perpendicular to the surface out. Okay, so what's the flux in that case? What's the flux of that vector? Very good, 0. That will be maximum. And here you will have to find the cosine between the normal force and the vector B. So what's going to be the, so if you take an imaginary bag, so it's closed bag, what's going to be the flux here?
The charge divided by epsilon zero.
Yeah, but
Oh, it's
0. Very good. And you see there is no charge inside. But it will be 0 because you have as many in that you have out. Okay, so let's find here. So this is just the mathematics. Okay, it's not Gauss law. Gauss law, we say the flux equals the charge inside over epsilon 0. Here it's just the mathematics found by Gauss, who was a mathematician. Okay, so why don't you try to do this? We can help each other. So that will be the number of lines poking through this invisible area. The area is not closed. It's not an easy concept because it's depends how you explain it. So this is the electric field, this is N, and you have an area A. Okay, so by definition, so we don't have to worry about the integral because you see here, E is uniform. How do I know it's a uniform? Because the space here is the same. So I don't need to divide my area in small element. I don't need to do that. I don't need to have those little scales here because the electric field is the same. Is the same. So when the electric field is uniform, you don't have to worry about the integral. Okay, so you just use the definition. Okay, so that will work if the electric field is uniform, which will be always our case. Okay, so that will be E times A, and the cosine between the angle between normal force and E. Okay, so the magnitude is 2 times 10 to the negative, no, not negative, 3 Newton per Coulomb times the area. So pi times 0.1 square times the cosine 30. Want to make sure here, so sometimes it can be tricky because you want to make sure you have the angle. Okay, the angle, to find an angle between the vector, you have to attach them by their tails. You want to make sure they are attached by their tails. It's fine here, but sometimes it can be tricky because if you don't do it right, you're going to find the sine instead of the cosine. What do you get?
54.
Okay, 54 Newton meter square per Coulomb. And we can, and that was the genius of Michael Faraday, who didn't go to school, didn't have a college education, but he visualized the field as lines in his head. Yes.
And he was really bad at math, right?
Yeah. Because he didn't go to school. At the time in England, the if you were not wealthy, you could not go to school. You had to work hard, like Dickens. I don't know if you know Charles Dickens. They will use the kids to do jobs that will kill them, like going through chimney to clean the chimneys, going through sewage. So he was very lucky. He went to work in a bookstore. So he taught himself science on his own, but he never went to college. So he visualized things. He did experiment, and then someone like Maxwell or Gauss, who were very good mathematicians, who were wealthy, so got an education because they were homeschooled, he translated the ideas of Michael Faraday into math. Isn't that a beautiful story? Michael Faraday. So anyway, it's a good point. So here we did that. Oh, and they say, what happens if they are perpendicular to each other? 0, right? So if n is this way, e is that way, nothing goes through, so the flux will be equals to 0. Yes.
The reason it'll be maximal flux is it because cosine just equals one, so the number is not getting lower.
Now it's
Zero in that case, because you want to find the number of lines poking through the surface, right? So if you have the electric field like this way, and you have your net, it's like a little net here, and you are finding how many lines poke through, it's going to be zero, because you see, and then n is this way, e is that way, this is 90 degrees, so cosine 90 equals zero.
When the disk is completely like straight up.
So yes, so that will be the maximum. So if the angle is zero, like this way, then you have the maximum.
Is that because it's like cosine 180 since it's a straight line?
So it's cosine zero.
Zero.
Right, so that will be n. So in that case, the flux will be E times A for the maximum one. Okay. Which is 2 times 10 to the third times pi times 0.1 square. Newton per Coulomb meter square. Okay? Yeah.
I'm sorry, I understand the math and everything. I understand. We just finished saying that, like, I'm probably just missing something. We just finished saying that in an open, like, space, as many lines that go into the surface come out, like, that means that it's, like, zero flux. How is it that in this case, if we have it, completely, like, perpendicular to, like, the electric field, how is it that there's, like, flux?
Because it's a good question, because this, in that case, I'm just doing the math. So, but the flux, the surface is not closed. It's gonna be in equals out if the surface is closed. So this is just the math. When we're gonna use Gauss law, we're gonna use a closed surface. So it means instead you still have the electric field going this way, and now we use a bag, like let's say a plastic bag, but let's say it's plastic bag like this, right? But it's closed. Now it's closed. It's a bag that is closed. So in that case, the flux will be equals to zero, even though it could be perpendicular to each other at some point, because whatever comes in comes out. So comes in equals comes out only works if you have a closed surface. This is just to understand the mathematics. So this is the mathematical tool. And then we're going to get to the physics that says if there is no charge inside, there is no flux. So in that case, what do they want? So just use the definition. So that you are looking at the phase C here. Just focus on C. Okay, it's just C. So just this. So the total flux through the cube. So it's a bag in the shape of a cube. Of course, going to be zero. But I just want through that phase here. So just use the definition. What's going to be the flux?
D.
C, right? Area you square. Here is a square. Okay, so remember, when you are finding an area, 4 pi r square, there is a square. Distance times distance. If you are distance times distance, that will be a volume. So the answer is C. Okay, so this is the same blah blah here. You can go through it. And then now you can have an integral. If the electric field is not uniform, okay, through the area, so then we have to divide the area in small, tiny elements here, and you have to sum up. You have to scan through and finding all the lines poking through. Okay, I will get back to that. Finally, Gauss law. Okay, apply to physics. So you see, if you double the charge here, does it make sense? You double the number of field lines, yes? So it's not a real thing. It's just to visualize. If the charge is negative, the line comes in. If you have twice the charge, in that case, you also have twice the number of lines. Agree? If you have a dipole, a plus or minus, how many comes in have to come out, right? Because you have coming in here, coming in, coming in, coming in, and then coming out from this one. So if you have 1, 2, 3, I don't know, 1, 2, 3, 4, 5, 6, 7, 8 coming in, you're going to have 8 coming out. So in that case, you have Q and minus Q over 2. So you're going to have half the lines if you have a bag. So you can show that here if you take an invisible. So this is I put that, like, people were crazy during COVID. Okay, I live in New York City. I've seen those people here in those hamster thing, but it's a tangent. But you see what it looks like. That's an imaginary bag. So if you take an imaginary bag around those charges, you see that the number of lines poking through, which is a definition of flux, okay, depends only on the amount of charge inside your imaginary bag. So you can visualize that. So for example, if you have a dipole, you have 2 lines in, 2 lines out. So the flux will be equals to 0. Very good. And the number of lines here will be twice this one because you have twice the charge. If you have this one, it will be half that one. Now, it doesn't matter what your bag looks like. It's imaginary. Okay, so this is called Gauss law. Okay, and I have so these videos come from Mechanical Universe. You can find the series on YouTube. It's very nice. It's from back then, but the music is weird, but the visualization, it's even before AI. They did a great job.
This law states that for any closed surface, the total flux is proportional to the net electric charge inside. If there's no net charge inside a surface, any positive flux outward through it must be balanced by an equal amount of negative or negative.
Okay, so you get the idea. Yeah.
Maybe a stupid question, but since in the dipole, it says it moves from the negative to the positive, right? Is there a reason why, like, on the pictures like I've seen, the arrows, like the vector arrows, are from like positive to negative on the like dipole, like right there, like I see that it's going from like
No. So don't confuse the dipole moment and the electric field. Okay, it's a good point. So the electric field goes always from plus to minus, always, or plus to infinity. And the dipole moment goes from minus to plus by convention. I don't even know if chemistry uses the same convention. I forgot. You have to check with chemistry. Okay, so the number of lines, so it's a closed surface, it's imaginary, it's in your head, will depend on the amount of charges inside that bag. Okay, so we can show that here. We can even so it's a consequence of Coulomb's law. So for example, if you have a positive charge here, right, and at a distance r, we have learned that first of all, the electric field here is perpendicular. See, the electric field is perpendicular. to the surface, it's parallel to the n hat. And it's uniform in magnitude. So the magnitude of the electric field here does not change because it only depends on the distance r. So we have seen that at a distance r from the source, the electric field is kq over distance r squared, right? So it depends on q and it depends on the distance. Okay, so we're gonna see what's gonna happen. Do the computation. See what's gonna happen if you multiply E by this invisible spherical bag. Okay, so you take an invisible spherical bag. Here it's invisible. It's a sphere. It's a surface. What's gonna happen if you multiply E by the area? So try to do that. So it's going to be E. What's the area of a sphere? Yes, 4 pi r squared. Okay, so it's going to be kq times 4 pi r squared over r squared. Is that right? Okay, so the electric field times the area is going to be kq 4 pi r squared over r squared. Okay? Okay, you go bye. Bye, nice meeting you. So K is also can be written as 4 pi over epsilon 0. That's another notation. So E times A is going to be KQ times 4 pi epsilon 0. Boom, boom. There is no more K here. Boom. So E times the area will be Q inside the bag, which is imaginary. It's called the Gaussian surface. It's called the Gaussian surface. And so you see that Gaussian law, it's just an elegant way to write a different way Coulomb's law. Okay? And epsilon 0. Okay, so then if you want to do the calculus, you don't have to take a nicely shaped surface. It can be weird, it can be an imaginary surface, but it's weird. But then you have to use calculus. You have to divide your surface area in small elements like scales and find the component of E parallel to the normal force. And that becomes an integral, double integral. Not only is double, but it's also closed. So not only it's a surface integral, okay, so surface integral, something, and then here you have dx, dy, but it has to be closed. So you do it this way. That means over a closed area. That's the meaning. That's the notation. It's closed. Right? Okay. So sometimes they do it this way. Okay, so you can write it this way or write it this way. It's Gauss law. That will be the unit for the electric flux. So what do you feel? So the flux only depends on the charge inside your bag. So if you have it's very good, it's not going to change. It only depends on what is inside the bag. You can have anything outside, doesn't matter. So it does not change, okay? So for example, so sometimes they ask you for the flux, and asking for the flux without computing the electric field. So the flux, using the physics, is just the charge inside the bag over epsilon 0. So if you want to find the electric flux through that closed area S, you're going to say that's going to be, what is inside?
Time 10 to the -6 divided by 8.81.
Yeah, exactly. Put a parenthesis here, Newton per Coulomb meter square. Okay, so that means they don't want you to find the electric field, they just want you to find the electric flux. Finding the electric field can be complicated because then you have to integrate, but you see that the flux will be positive because it's a source. Here you're gonna get the same thing but with a negative because it's a sink. Okay? So think about it. Let's say this situation, what's going to be the electric flux through that invisible cube? It's a surface, but it's like a cube.
The sum of the charge inside.
Yeah, so what's the charge inside? 0.
Oh,
Yeah.
it's 0.
Because you're going to have as many things going out and 1, 2, 3, 4, 5, coming in. Okay, it only depends on the charge inside. In that case, it's going to be 0. Agree? Now this one, what's the charge inside? Plus 1, right? So it's going to be 10 to the 6 divided by 8.85 times 10 to the negative 12. Newton per Coulomb meter square. So here they just ask you the number of lines poking through. If you want to find the electric field, then you have to pull your hair and divide the surface in little scales, a little square here. And for each little one, you have to find the component of E parallel to the normal force, and you have to do the sum of E parallel to the normal vector, times delta A, and that becomes like a closed dA. Okay, but we'll never do that because you have computers to do that. You will use a code. Yes.
10 to the -6.
10 to the negative 6. Yes. Micro. And then it says textbook. I forgot what's in the textbook that I said. Textbook. So Gauss law, blah blah blah. Okay, so they explain to you that the number of lines poking through this is an area here, the same here and there, as a consequence of Coulomb's law, the inverse square law. Okay, so it's just Coulomb's law, but written in a very elegant mathematical expression. Okay, so they show you if you have a bag here and the shape is weird, you're still gonna find the same number of lines poking through, but the math is more complicated. Alright, so they tell you all that, so you should go and go over the textbook, blah blah blah, blah blah blah, blah 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 blah. Here you have a dipole, so you have the same number of lines going in, going out, so it's going to be 0. And they give you some applications, Gauss. Okay. So the book is very nice Spanish. Okay, okay, okay. Okay, okay. Okay, okay. So something that you remember, that you have to remember, is that if you have a conductor, so it doesn't have to, it could be a shell or it could be something solid. The charges never stay inside, they always go outside. Okay, it's always going outside. And they spread out on the surface. Now, in that case, it's like the Van Graaff generator. So it's called a shell. Okay, so you have a Van Graaff generator, you charge it, you crank it. So you have all those charges spreading out uniformly because you have a nice symmetry. The electric field in magnitude will be the same because it depends only on the distance. Will be the same on the surface here. It will be the same on the surface and it will be perpendicular to the surface. Okay? So we're going to use, very easy, we're going to use Gauss law to find the electric field outside and inside. So let's say this is a Van Graaff generator. So it's not imaginary. And so you have a sphere and all the charge spread out on the outside. There is no charge inside. It's forbidden. No charge inside the conductor. So the electric field is going to be the same at a given distance. Here it's going to do something like this. Okay, and this is r, the radius. So I'm going to take at a distance, I want to know the electric field here at a distance r. So you use the symmetry. You're going to say, okay, I'm going to take an imaginary bag. This is my imaginary bag. It's like a plasma globe, right? It's spherical, right? And I'm going to say the electric flux, okay? The flux of the electric field. So the number of lines poking through equals E times the area. Okay, so the area will be this. We already did that. But you see, even though it's not a point charge, it's a Van Graaff generator. The charge inside is just the charge of the Van Graaff over epsilon 0. So now I can use Gauss law and shows that the Van Graaff generator will behave just like a point charge. So the number of lines poking through here only depends on the charge that I have on my Van Graaff generator. Do you agree? And then it's easy, right? So you have E will be equals to Q in over 4 pi epsilon 0 r squared. That will be for r equals or greater than r. Agree?
Why is it 4 pi times r squared?
Because the area of a sphere is 4 pi r squared.
But I thought it wasn't I thought Gauss's law wasn't dependent on, oh, because we're finding the electric field, not the flux.
Yes, Yeah,
Oh,
we are not finding the flux. We are using the definition to find the electric field, poking through, and the same electric field at a distance r. Agree? Okay. So what's gonna happen if now you are inside the Van Graaff? So if you are inside the Van Graaff generator, so you have your Van Graaff generator, but you are inside. Okay, so now I'm going to use Gauss law to see what's going on inside. So I take my imaginary bag here. I'm going to do the same thing. Okay, so we have the electric field times the area, 4 pi r squared. But what is inside? Is there any charge inside? No. So what is the electric field inside? 0. So inside the conductor, there is no charge and there is no electric field. This is called a Faraday cage. So if there is a storm outside, for example, you have lightning. So let's say there is lighting outside, you are inside the car here. I don't know how to make a car. I'm going to do like kindergarten. Okay, this is my car. That used to be my car. If you are inside here, the car, and you have lightning, zoom. So what's going to happen? The charge will always stay on the outside and you're gonna be safe inside as long as you don't step out. So what you don't want to do is to open the door, touch the door, and step in water. That will be very bad because all the charges don't like to be here and they are kind of insulated from the ground. So you offer them a path to the ground. That's how you're going to be electrocuted. But as long as you don't touch the chassis of your car, you're fine. It's called the Faraday cage. So inside the conductor, even though you can have some opening, not too much, right, like a frame, you're going to be safe inside because the electric field cannot go inside, the charges cannot go inside. They will rearrange themselves such as they're gonna move away from each other as far as possible. Okay, so this is called the Faraday cage. And I have a picture somewhere. Okay, so you can do those. So this is at the Boston University. So not university, museum, Boston Science Museum. They have those huge Van Graaff generator because they used them as particle accelerators back then in the 30s. Van Graaff generator was invented by someone from MIT to make accelerators. So then they were donated to the museum. And you see it's going to discharge here because it's going to find a way to the ground. But the guy inside is safe. You just don't want to touch the cage, right? But inside it's going to be safe. However, his cell phone, for example, is not going to work because the electric field cannot reach his cell phone. Okay, so radio wave is made of an electric field and a magnetic field. So this is called a Faraday cage. See, Faraday cage, you're fine. He has special thing on his ears because it's going to make a very loud noise, but he's safe. And this is a Faraday cage.
We are electrified before I actually know what's going to happen. Sounds by let's see what the ground.
So this is connected to ground. There is lighting hitting him, but he cannot go inside because he has like a special suit made of metals. and the electric field cannot get inside, the charge cannot get inside, and the charge wants to go to ground. So you have a breakdown of the electric field in the air. Okay, so the air get ionized, electricity is flowing, wants to go to the ground. Yes.
Noise.
It's I don't know, it's
Is it vibrating?
I don't know, maybe I'm not sure. So maybe it's the machine, the power supply that makes electricity. I'm not sure.
It's like lightning also like doesn't really thunder. I guess thunder makes noise. But I don't really know what it is.
But that in that case it's bzzz. So maybe you know what it could be? It could be a transformer. The transformer make noise like this. If you have very high voltage and it's AC, it's gonna do bzzz. It's buzzing. So a lot of application, you see here, you save inside. So all those, like if you take a USB cable and you, from the dollar stores, a cheap one, you cut, you're gonna see a fold. If I cut this USB, I'm gonna see a fold here. That fold is a Faraday cage to isolate the signal from the outside noise. Okay, so it's isolating it. So whatever is inside, that's the principle of a Faraday cage. Whatever is inside, it's ignoring the outside. You do whatever I want. You know, there is, even if you have a stray electric field, it's not going to affect the signal. And you can do that. Like if you take a USB here, right, and you cut it, you see what's inside, you're going to see the foil. So it's a Faraday cage to isolate the signal from the noise from the outside. You can see that here, right? So here you have two electrodes, plus and minus, and you see you can visualize the electric field from plus to minus. You can see that the electric field is perpendicular to the surface. It's always perpendicular to the conductor, and the magnitude is uniform. You see, it's uniformly spaced out equally. But inside, I don't know if you can see inside, there is nothing going on, because there is nothing inside a conductor, even though it's in, I guess it's in 1D now, right? There is nothing, there is no pattern. So to go back to finish, now we'll open here. So for this one, you see if you do a graph, electric field versus the distance, inside the conductor, inside the Van Graaff generator, the electric field is going to be 0. Okay. And then here, it's going to be that. Okay. So it's going to be Q in over 4 pi epsilon 0 r square. And as you move away, it's an inverse square law. So that's going to be 1 over r square. So it's, I don't know how you call that in math. It's not continuous. There is a discontinuity here. Okay, it's vertical. And I forgot my math. It's point of, I forgot. But there is an issue here. Okay. Okay, so if you are very far, if you are outside the Van Graaff generator, so then it will be, the electric field will be proportional to 1 over r square, okay? Inverse square law. Inside, the electric field is going to be 0. So if you have a conductor, even though now it's a volume, it's solid, okay? Like the Volta, the John Travolta simulation, the The charges always move on the outside the conductor. It cannot stay inside. It's forbidden. Cannot stay inside. So what's happening if you have a spherical shell and you have the charge on the outside? If you double the charge, so if you crank the Van Graaff and now the charge is multiplied by 2, is it going to change inside? No, because there is no charge inside, there is no electric field inside. No matters what's going on the outside, inside, ignore the outside. That's why it's called a Faraday cage. Okay, so the Van Graaff generator, which was an amazing invention, because you see here you have some friction happening, and then the charges go up, and then here there is like a little comb. Okay, it's like a brush, metallic brush, and all the charges, they refuse to stay inside. They say no, 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 no. We have to go on the outside. They move outside. And then you keep charging, and at some point, you cannot take it anymore because it has a given capacity for holding charges, and then you have a discharge, and then they want to go back to ground. Okay, so this we already discussed that. Okay, there is so much you can take today.